Hello everyone. What's up? सर अमीर नहीं हो गए, सर अमीर लोगों के घर में आके सेशन ले रहे हैं आज. ओके. सर बड़े लोगों के घर में आके लेक्चर ले रहे हैं आज. Where Suri sir should be partying, he's actually taking class. I should be partying, but now then there is Drishti JEC batch to be taken. Exactly. Guess whose house is this? I am in Bangalore. That's one hint for all of you. Whose house is this? Yeah, Ambani does not live in Bangalore. He lives in Mumbai. All of you know that. Shimon sir also does not live in Bangalore. Exactly. This is your captain's house. This is Harsh Maheshwari sir's class. Sorry, not class, but house. He's taking a parallel session somewhere in another room, by the way. He's taking his own session. Otherwise, he might be like photobombing right now. Okay, so can't call him right now. Obviously, he's also taking a class. Okay, he has his own class here. He teaches other batches also, right? So that's why. We'll see. We'll see. Okay, we have seen the balcony behind. Okay, so you guys have seen this background already. That's nice. Harsh sir is very rich. Absolutely. Suri sir is not so rich. He's poor. But then all of you guys are definitely able to make it out that the kind of house he has into. Cool. Nice. Suri sir's uncle is Ambani. I wish यार अगर मेरे अंकल अंबानी होते तो मैं डेफिनेटली कहीं और ही होता नहीं. ठीक है, everybody's ready. Shall we start? फिर बाद में बातें करते हैं, maybe if required. और आज जल्दी खत्म करेंगे as always. No? Rather, never always. We never finish our session before time. We always have taken our session up to the time that is given to us, right? ठीक है, तो आज कोशिश करेंगे थोड़ा जल्दी खत्म करते हैं so that me and Captain would like to catch up a bit. ठीक है, everyone is okay with that? Everyone would be okay with that? Finishing up a little early. ठीक है, for a change, obviously next week you will find me with the usual background, है ना? चलो, awesome. Thank you so much, guys. And meanwhile, quickly today for a change you have only one class teacher, Mrityunjay sir. Quickly say hi to your class teacher, everyone. Everyone? Yes. Awesome. Very good. Quickly say hi to your class teacher. Great. Thank you. Hi, Mrityunjay sir. Welcome to the class. Okay, great. So everybody, this is our session number 4. Okay, and in session number 4 of fluid mechanics, we'll be today speaking about a much awaited topic. We'll be speaking about the bind force, Archimedes principle. Okay, finally the Eureka moment comes in. Okay, you remember how many of you have heard about the Eureka story? मुझे याद नहीं है. I have forgotten, but I only remember Eureka. Okay, Eureka means I have discovered something. It's like finding something new. Okay, so definitely you can Google today the Eureka story after the class. Absolutely, bathtub story. Yes. So guys, we'll be speaking about that today, but a quick recap of what we did last time. So I hope you people remember last time also we did very few topics to cover. We spoke about if there is a container, my usual bottle, it's always there. Okay. So this one will be rotated, and if it is rotated, the liquid surface will no more remain horizontal. Rather, it will take a parabolic shape. So if I want to find out that from the axis of rotation, if I am at a distance x, how much height the liquid has gone up by. Okay. मेरे साथ 24/7 रहती है. Absolutely. This is my water bottle. COVID आने के बाद से तो मैंने बिल्कुल बाहर किसी और बॉटल को हाथ लगाना भी बंद कर दिया. So this is the height to which your liquid rises. That is given by omega square x square by 2g. सबको फॉर्मूला याद है. Though we did the derivation also, that's a very easy derivation. Okay. Okay. Yeah, so everybody, we spoke about this part first, and after that we spoke about the Pascal's law. Switching off the chat now so that we all focus on screen. Class teachers, I will take care of that myself. Please do not forward those messages to me. Okay, so according to the Pascal's law, so that was the first thing that we studied. That was when we have like a liquid rotating, or the container rotating and the liquid making a shape of parabola. The second thing, which was more important, we spoke about that, and that's Pascal's law. We understood that if we neglect the effect of gravity, then if you ever change pressure at any point in the liquid, then the pressure is going to change by the same amount everywhere. That is what is a very important conclusion that came from Pascal's law, that the change in pressure at any point is confined incompressible liquid. Obviously, we're speaking about ideal fluids. So the liquid is going to be under the same pressure at any point, the change is going to be the same. Okay. Also, the pressure exerted at any point is same in all the possible directions when the liquid is at rest. And the application of the Pascal's law was studied in the form of hydraulic lift. And the concept was very simple, that the pressure at 2 points are going to remain the same. So maybe if I'm keeping the pistons which are going to lift a vehicle, so all I need is like different areas of cross section. If I have different areas of cross section, A1 and A2, then the force that I'm going to require to apply the same pressure, that's also going to be same. If area of cross section is more force can be sustained or can be balanced by applying a very small force F1 on area A1. Okay. Also, the pressure in liquid is same at all the points in the horizontal level. This is something which I taught you guys in the very first session itself. Okay. Also, the other point also I taught you in the very first session, that the liquid pressure is independent of the area and the shape of the containing vessel. So these are 2 points that we covered like in the very first session itself. Okay. Everyone is okay with this? We spoke about like 2 topics only last time. Today also we have very few topics to cover. Only buoyancy is the major thing that we want to cover, and the condition for an object to float. So let's quickly go through a quiz which is based upon the topics that we covered last time. I hope that you guys will be able to answer this one quickly. This one, it says that there is an assertion reason question, and the assertion. Okay, these are usually the kind of questions which you don't expect in JEE. They used to come in only NEET examination, but now JEE also has started incorporating questions like that. So assertion means the statement number 1 says that the Pascal's law is the working principle of hydraulic lift. Okay, and the second one is the reason of the assertion. The statement 1, the reason, it says that pressure is equal to thrust per unit area or force per unit area. So what you have to judge as per options. Option A says that the assertion is correct, reason is also correct, and reason is also a correct explanation of the assertion. Okay. Point number 2 says that both assertion and reason are correct, but reason is not a correct explanation of the assertion. Both are correct, but it's not explanation. Third one, assertion is correct, reason is not correct. Fourth one, assertion is not correct, reason is correct. Okay. Now because this is the very first time I do not remember any of the assertion reason questions being done earlier in our class, that's why I give you guys 90 seconds to redo the thinking of assertion and reason and think whether there are truth or false in it, and if there is truth, then are they really related to each other. Giving you 90 seconds, and the time starts in 3, 2, and 1. Nah, the background is not good. Okay, guys. So now the last 5 seconds are here. Let's see how many of you guys are able to answer this one. This is little, I know, this is on a gray zone also. So many people might have thought of the answer to be option A and might have thought of answer to be option B also. But let me tell you, if you read reason first, it says that pressure is equal to thrust per unit area, right, everyone? And we all know that that is true. Even before we came to know about Pascal's law, we know that statement number 2 has been true. Correct, guys? Statement number 2 has already been true. But we never said that that is the reason because of which Pascal's law works. Pascal's law tells us that in a fluid, the pressure, which we know how it works, is going to be transferred equally. So definitely, the reason is not the correct explanation for the assertion. Okay, cool. Yes, 3 teachers under the same roof. Okay, so everybody, let's start our today's discussion. Today's discussion is confined and is based upon the Archimedes principle. One is buoyant force, the second one is going to be an application of the buoyancy known as the flotation. Okay, everybody? I know. You might be hearing him taking a session in the background. I can totally understand that. Thrust is basically force only, nothing else, Karthik. Okay, so everyone, I hope you people are there in our session number 2, I guess, when I gave you guys already an idea that how buoyancy comes into picture and buoyancy creates a force which is only upward. Are you guys aware about that session? Were you there in that class, everyone? I told you guys that in a container, say in a liquid, say I have another container which is placed. This one will have a pressure P1, this one will have, or the top surface will have a pressure P1, bottom surface will have a pressure P2. And force due to this liquid pressure is always going to be perpendicular to the surface. So if we look at the forces which are applied, one of them is downward, one of them is upward. And we know that P2 is greater than P1. You all know that. And we also know that in that case, F2 will also be greater than F1. And what is the direction? What is the direction of F2 minus F1? What is the direction of F2 minus F1? Up or down? It's definitely upward because F2 is greater than F1. And this force appears as the buoyancy. So this is the fundamental that I want you to be able to remember. I want you to be able to remember this concept. Okay? Okay. So switching off the chat so that we all focus on this. So we'll be now speaking about the buoyant force and the same derivation we'll be doing formally now. So say you have a liquid inside which you are considering an imaginary water body. Okay, this is actually made up of, say this is basically water that we are talking about, and this is basically a fluid body or water body itself. That means what? It's an imaginary cylinder that I'm talking about. So if we speak about this, or we can also actually talk about a body which is completely submerged also, or maybe just submerged here. So first of all, though the definition has to come in the next slide. Okay, so I'll first take you to that part and then we'll come back to this one. Okay, everybody. So what exactly is buoyant force? We know that buoyant force is basically the upward force which is applied by the liquid force, or the force which is applied due to difference in the pressure of the liquid and acting in the upward direction. So this net upward force which is experienced by every object which goes in the fluid, doesn't matter whether it is highly dense or lower dense than the liquid, doesn't matter. Let me tell you that. If the body is wood, it might float. If the body is made up of iron, it will sink. Does not matter. The body, as long as it is in the liquid, it is definitely going to experience an upward force. That is a different thing. That how much portion of that body is submerged in the liquid, that is the one which will define the magnitude of the buoyant force. So I hope you people remember this from the earlier classes, but if you don't, then that's totally fine. It's basically when a body, the statement says that whenever a body is completely or partially submerged in a liquid, submerged means it goes inside like a submarine. Okay, so it is always going to experience a net upward force. The magnitude of that net upward force is going to be equal to the weight of the liquid which is displaced. So just look at the diagram once. So if this is basically the body which is going to be accommodated here, can I say that to accommodate this body here, the liquid has to come out of it? So that is why even Archimedes did the same thing. He took a container, he was in a bathtub at that point in time, which is completely filled with water. If you are going to put any object inside, the volume of that object has to be accommodated inside the liquid. So to accommodate that body, the water of the same volume has to come out. So that's why we say that the amount of volume of the body which is submerged is equal to the amount of the volume of the liquid which goes out. So when we calculate the buoyant force, it turns out that the amount of weight of the liquid which is coming out is equal to the buoyant force which is experienced by the body in the upward direction. So I'll come to this formula while doing the derivation also. Okay. Remember, again, once again, I'm telling you that it is because of the pressure difference between the top and bottom point of the body. So if we look at this diagram once again, so okay, so I'm removing this to be the water body or anything. Let's not call it a water body. It could be like any liquid. So if we say that there is a body which is submerged, whose length is maybe known or may not be known, that's totally fine. So it is having its top surface at a depth h1 and its bottom surface is at a depth h2. Because of that, there is basically the pressure difference. And the force acting on the top surface is P1 into A. A is being the area of cross section of the body itself. So P1 into A becomes h1 into rho into g into A. Right? So P is basically h rho g. Multiply that by A, you get the value of the force F1. Similarly, you get the value of force F2 also, which comes out to be h2 into rho into g into A. Okay, everyone? As we know that pressure P2 is greater than P1, you all understand that very well. As we go more and more in depth of the liquid, the pressure increases. And as the pressure increases, the value of the force also increases. Okay, everyone? So that is why F2 is greater than F1. And everybody, look at the body. If it is at rest, then the body can be at rest only when the net downward force is equal to the net upward force. So you can see that the downward force is F1, downward force is mg, and the upward force is only F2. So we can say that F2 is equal to F1 plus mg. So we can say that F2 minus F1, which is basically the buoyant force, is equal to the weight of the amount of the liquid which is being displaced outside. Okay, so we can write the weight of that liquid as density into volume of the liquid which is submerged into the g value. I hope that you guys are getting that how this mass is coming out to be. This is mass of liquid which is submerged. Okay, everyone? Fine, everybody is okay with this. So remember, the formula is rho into V into G. Yes, the formula is something that many people remember. It is rho into V into G. But density is of the liquid. Volume is of the liquid which is displaced, which is equal to the amount of body's volume which has come in the liquid. That means what? If I'm trying to put a solid body inside and only half of that body is inside the water, so only half of that volume of the body is taken into account. So if the entire body submerges, then things are very, very good. Then things are very easy because entire volume of the body is equal to the volume of the liquid which is also coming out of the container. Okay, so this is what has to be taken into account. So rho into V into G when we write, this is the formula which I said we'll be looking at how the derivation comes. So it is rho liquid into V body submerged or V of the volume of the liquid which is displaced. Are you guys able to understand this? Though we kind of got the idea in the previous 2 sessions only, but now the formula is there in front of us. So when you're remembering the formula, remember when you're writing buoyant force as rho Vg, rho is the density of liquid, V is the volume of the liquid which is coming out, which is submerged, or the amount of volume of the body which is coming in the liquid. Okay, awesome, very good. Yes, absolutely. Okay, so everyone, now what did Archimedes do? He said that whenever a body is fully or partially submerged in a liquid, it experiences a net upward force which is equal to the weight of the liquid displaced, which we have already seen. This is basically how he could calculate the amount of weight of the body which was trying to be submerged. He basically tried to check whether the gold ornaments which are being given to the king, are they pure or not. So basically we know that the amount of liquid which is displaced by the solid body which is completely submerged, if that weight comes out to be equal to what the pure weight of a gold ornament has to be, because density of gold was known to us. So gold density into volume should be a mass value that we know. Same amount of mass value should come out to be of the liquid which is being displaced. That's why he could figure out whether the gold ornaments are having any cavity or do they have any kind of impurities mixed in it. Okay? Because if gold ornaments are mixed with any impurity or more than the desired amount of impurity, then their weight increases. Okay. Are you still here? Are you still here? Am I still connected to all of you? This is new for me because that's one thing which we don't have in Mumbai. This is one thing which never happens in Mumbai, you know that. Mumbai will never have a power outage, right, everyone? You want to know that this is common in Bangalore. So let's carry on, everyone. Okay, cool. Yes, captain is taking a class. Okay, guys. So basically, again and again restating the same thing. The force exerted by the liquid on the solid immerse sums up the upthrust and the buoyancy force, and it always will be acting vertically upward. It will be equal to the force exerted on the top and the bottom. Bottom part will always have more force because more pressure is there at the bottom of the container, and it acts through the center of gravity of the displaced fluid. That's what this thing is. Let's try to see questions, solve questions to understand this thing better. Okay, everyone. So let me first give you guys the question to try. Question comes on the screen. What do you think? Does air apply a buoyant force? Do you think air will also apply a buoyant force? Giving you guys 30 seconds to answer this, and your time starts in 3, 2, and 1. Come on, everyone. Let me see if my mobile phones. Should I use this? Though it's highly irritating right now to use my mobile phone's flashlight. Okay, and the time is up. So is air a fluid? The first question that you should be asking yourself. The first question that you should be asking yourself is air a fluid? First question. Everyone. So if it is a fluid, it definitely obeys the laws which are obeyed by the fluid. Okay. You say that air is not fluid. Come on. In the very first class, we understood that liquid and gases both are considered to be, okay, both are considered to be the same. The fluid. Okay. Okay. Guys, is it okay if I don't use this flashlight for some time? Because it's actually highly irritating. I might have a headache because of that. Okay. Just for today, you know that it's a temporary arrangement today. So that is why. Okay, so the correct answer, thank you so much, everyone. Correct answer is yes. Air being a fluid does apply buoyant force. Air is also a fluid, so applies buoyant force on objects. Okay. Yes, absolutely. Okay. This is not his usual laptop sound. Yeah, actually, it's more of surroundings. Acoustics are different. Acoustics are different. That's why. Okay. Acoustics are basically things around you because of that sound reflects. We will study that in waves, by the way. The next chapter will be sound. There will be a little bit of echo also right now. Okay. Yes. So switching off the chat so that we focus on the screen. So guys, now comes the proper question on buoyancy or buoyant force. It says that we have a block whose dimensions are given to us as 4 × 5 × 5. So it has a square base. Okay, so maybe not my mobile phone actually, but properly a square base. This is 5, and this is 4 centimeters. And its density is also given. And the density of the liquid in which it is placed, it is maybe floating, half submerged it is 900 kg per meter cube. So we have to calculate the buoyant force applied by the liquid on this. G value is given to us. So everybody knows, first of all, that the buoyant force will be acting upward. And the magnitude of this buoyant force is going to be rho of liquid, volume of the liquid which is displaced. Or you can say that the volume of the solid body submerged. How much amount of solid body is submerged into G value. Okay, everyone. So the density of the liquid is 900, or I will write it as 9 into 10 to the power 2. Volume submerged, I want to find out separately. Okay, everyone. So you can see that this blue portion that you see here is the volume of the solid body which is inside the liquid. So the volume of that is 2 into 5 into 5, but this is centimeter cube. I want to convert it into meter cube. So it will be 10 to the power minus 2 into 10 to the power minus 2 into 10 to the power minus 2. So 10 to the power minus 6 meter cube. That's basically the volume. So 25 into 2, that becomes 50, or I can say 5 into 10 to the power minus 5 meter cube. That's basically the volume. Okay, guys. And we can write it as 5 into 10 to the power minus 5 into G, that is 10. So we have 45 into 10 to the power 3 into 10 to the power minus 5. This gives me the answer as 45 into 10 to the power minus 2, or 0.45 Newton is the force as the buoyancy creates on this body. Okay, everyone. So the answer is going to be option A here. Okay, everyone understands? By the way, now because there is a power cut and my laptop's battery is going to play a very crucial role. आज कितने slides हैं? Close to 60 slides हैं. ठीक है, it is already on power saving mode, by the way. Okay, thanks for the suggestions. Anyway, चलो guys, now I think questions for all of you guys to try. The answer is something that we've got. Okay, so यार ये ना कुछ ज़्यादा ही brightness कम हो गई है जिस वजह से मेरा ही चेहरा तुम लोगों को दिखाई नहीं देगा. Anyway, yes. So everyone, the question for all of you guys. So if a body has an actual weight of W in air, that means if you place it on a weighing machine, it weighs W. Okay, and if I dip that body in a liquid, okay, if I dip that body in a liquid, what do you think will be its apparent weight? What will be its apparent weight now? That means say maybe you are hanging a body by a spring balance. There is a spring balance of it, and you are holding a body. So the reading of the spring balance says that the body is W, having a weight of that. If you dip this body in a liquid, it starts experiencing a buoyant force. Now the reading is definitely changing. So how much do you think that reading is going to be? Giving you guys 30 seconds, and the time starts in 3, 2, and 1. Will the apparent weight be more or less? Will you feel lighter inside the liquid, or you will feel heavier inside the liquid? It depends on that. Okay, everyone? You must be getting the background noise, which is not a noise, which is basically Catherine taking a class parallelly. Okay, so let's see. That's good, guys. Nice. Great. So correct answer is option B. So see here, if you think that the spring balance was holding a body like this, and the reading was basically the tension in the spring. So the tension was actually reading W. So this was the reading. Now what happens? The same body is submerged in a liquid. So what happens because of that? The W is still acting downward. The tension say becomes T dash, but there's an additional force, buoyant force, which is acting on it. And the reading of the spring balance is T. So now it becomes T dash. We can say that the upward force is T dash plus buoyant force, which is equal to W. So can I say that now the new reading of the weighing machine, spring balance, becomes W minus Fp? Or any which way you can think it from the common sense also, that the apparent weight of the body has to be less than its actual weight, because when you go inside water, you feel lighter. Okay, so that's why the correct answer comes out to be option B. Okay, another question over here, which is ideally a quiz, not a quiz question, but I am setting it as a quiz question for all of you. The question says that the weight of a rock in air is 0.85 Newton. So when it's completely submerged in water, its apparent weight is 0.45 Newton. So what do you think is the buoyant force which is acting on this rock? How much do you think is the buoyant force which is acting on this rock? I hope that this should be very easy for everyone to do. Giving you 45 seconds for this should be easily doable, and the time starts in 3, 2, and 1. Come on, everybody. Last 20 seconds now. Okay, and the time is up. Let's see. Very nice, very nice. So last question is what is the numerical question based upon the same. Okay, so awesome. Should be easily doable. W dash is going to be W minus the buoyant force. So buoyant force is going to be the original weight minus the apparent weight. Whatever is the weight from that, the force which is acting upward so that now it feels lighter is the buoyant force. So that is 0.85 minus 0.45. So this value comes out to be 0.40 in Newton. Hence the answer comes out to be option C. Okay, everyone is comfortable so far with the concept of buoyancy? Okay, cool. Yes, thank you. Okay, जो सामने मेरी लाइट थी वो ऑन हो जाएगी अंशुम. There's a huge big light which is in front of me. तो अगर लाइट आ जाएगी तो that will glow. That's how I get to know. Yes. Okay, everybody. Moving on to the next topic, that is the condition for flotation. Condition is very simple. Though we know this from the densities point of view, if the body which is trying to float in the water or in a liquid has a lesser or equal density as that of liquid, it will be able to float. But if its density is more than the liquid, it's going to sink in. Okay. So if in terms of buoyant force we speak about, it's simple. The law of flotation states that the body will float in the liquid if the weight of the liquid displaced, that means the buoyant force, okay, is equal or greater than the weight of the body. If you are able to possibly create an equal or more possible force upward than the weight of the body is going to float. That's how simple it is. So maybe for a partially submerged body, if you submerge the body further down, the body will have more volume inside the liquid, the body will have more buoyant force acting, so body will be pushed more upward. In fact, have you guys ever tried this inside the bathroom with a bucket full of water? Have you tried to take the mug and try to put it upside down inside water? Have you tried to do that? Or usually normal way, if you will put the mug inside the water, do you know how much effort it takes to do that? You might have played like many number of times. I don't know. I thought that it was only our childhood thing. So that resistance that you get, when you try to dip it further down, is basically the buoyant force increasing. Why the buoyant force is increasing? Because you're submerging more volume of the container. If you submerge more volume of the container, you are basically making more water displace. If more water displaces, more buoyant force exerts in the upward direction. Got the basic logic, everyone? Cool, right? So simple as it is. This is something that we saw in the class 1 or 2 only of this one. The liquid, if it has lesser density than the body, then the body is going to sink. And if the object has lesser density than the liquid, or equal maybe, the body is going to float. As simple as that. And for floating, can I say that buoyant force has to balance the weight of the body? Do we agree on this? If the buoyant force is able to balance the weight of the body in any which way, then the body is going to float. Otherwise, the body is going to sink. Okay. So simple as this, that if the weight of the body is equal to the weight of the liquid displaced, which is basically the buoyant force, then if the body is naturally able to sink in, Monish, like a mug floats with not entire volume submerged. When you have something which is very light, entire volume does not go inside water naturally. So if you push it further, then you are increasing a downward force. So that will result in another upward force. Okay. Ball, plastic ball, same with plastic ball. Understood? Right? Fine, everyone. So the weight of the body here, rho is liquid density. Okay, everyone. Rho is liquid density and sigma is body density. So if I want to write down the weight of the body, it is mass into m into g basically. So m into g can be written as density into volume into g, and we already know the value of the buoyant force. It is v dash rho g. V dash is basically only the submerged volume of the body. May be equal to v, may not be equal to v also. Especially in the case mug wala case, v dash is going to be less than v in that case. So g gets cancelled. When g gets cancelled, v dash by v is equal to sigma by rho. So we can say, see, I don't want you people to memorize the last 2 lines. Only thing that I want you people to pay attention to is this one: that the buoyant force should be able to balance the weight of the body. Can you people, do you guys understand this logically? I don't want you people to memorize anything on second or third line. I want you people to logically understand that buoyant force acting upward has to balance the weight of the body. If it is successful, the body floats. Otherwise, it doesn't. As simple as that. Right? Awesome. Great. So what's the good part today? What's the good news from here? Theory over. Theory over. Not kidding. I'm not omitting any slide for today. I'm not actually omitting any theory for today. Theory is actually done for the day. Okay. So do aquatic animals experience buoyant force? Riddhiman, do you not know how to swim? Have you ever been inside water? When we go inside water to swim, do we feel lighter or not? Do we feel lighter or not? Why do we feel lighter inside water? It's because we are also animals, and even the sea animals are also animals. We both experience the upward force. Any object which has mass, which has density inside a liquid will experience a buoyant force upward. Yeah, including Nemo. Okay. So everyone, let's not get deviated. My laptop's battery is almost on 40% now. Okay. So let's first start with an example here. It says that a block of wood with a dimension of given to us, 12 centimeter to 34 centimeter to 43 centimeter. So 12 is to 34 is to 43 or 0.12, 0.34, 0.43. It floats along the river with the biggest face facing downwards. Just a second. That's not even my phone. Anyway, so basically what is happening, a block of wood whose dimensions are given, it is floating on a river with the biggest face facing downward as per the diagram. The wood is submerged to a height of 0.053 meters. So this is the amount by which it is already inside. So we can find out the submerged volume already. So what is the mass of the piece of the wood? How much is the mass of this thing? So very simple it is. Because it is floating, we'll say that the buoyant force is balancing the weight of this thing. That means mg. So buoyant force is only going to be corresponding to this volume, while the weight is going to be corresponding to the entire volume of the body. Okay, that's basically the only catch where many people make mistakes. So when we write FB, we will write it as rho liquid into volume of the body submerged into G value, while the weight of the body, when I'm going to write it as density of the body. Okay, and its density is not given and we don't even need it because this is going to be mg, as simple as that. So we don't even need it. We just need to find the mass of the body. Good. So we'll equate these two forces. G gets cancelled. So density of the liquid into volume of the body submerged. That's all you have to calculate. Okay. So guys, we know the dimensions are given. So if we calculate the area of cross section, 0.34 multiplied by 0.43 comes out to be 0.1462. That's the area of cross section. As I said, we need to find out only density of the liquid multiplied by volume submerged. G gets cancelled. So mass comes out to be this 10 gets cancelled with G. I need to multiply the density with the volume. So this is area of cross section, and this is the height of the body which is inside the liquid. That means this is H. So multiplying 0.1462 into 0.053, multiply that by 1000, you'll get the value as 7.75. Definitely calculated, but is the concept clear to everyone? Do we understand this? Simply what we did, we equated the buoyant force with the weight of the body. G got cancelled, only thing that we calculated was density into volume of the submerged part. Okay. So what happens when area touching water is less, then will this be characteristic for floating? What happens when area touching water is less, as in? Area, as in we are more concerned about the volume submerged. Doesn't matter, you can always calculate the volume, na? Can we not calculate the volume of the any shape of the body which is inside the water? We only need that volume. It doesn't matter how much area is in contact. Doesn't matter. It's only about the volume of the body which is submerged. Okay. Understood? So whatever the shape of the body, it doesn't matter. Okay. So the sea animals will have more blood pressure. Yes, definitely. Sea animals will have more blood pressure because apart from atmospheric pressure, they are getting the pressure of the liquid column on top of them. That's a good question. Good point actually. Okay. So density of the body gives then previous formula. Then we can. But in that case, they will not ask for the mass. They will ask for maybe the volume of the body if the density is given. But they are asking for the mass, so we don't need the density of the body. Okay. Cool. So we should consider only the submerged part. Yes, that's what the entire concept of buoyancy is. Okay. Cool. Taking you all to a question which is ideally a non-quiz question, but I'm going to set this up as a quiz for all of you guys. Okay, everyone. So read the question. Setting it up as a quiz, and let's understand what it is saying. It says that a cubical block of side 0.5 meter floats on water with 30% of its volume underwater. So only 30% of the volume is inside water, 70% is outside. So if the volume is say 100 centimeter cube, so only 30 centimeter cube is inside, 70 centimeter cube is outside. So what is the maximum weight that I can put on the block? If I keep on putting more and more and more weight, the body will have more mass, more weight, so it will start sinking in. So what is the maximum weight that I can put so that the body just gets submerged, completely submerged? Okay, when they say that, what is the maximum weight that can be put before it gets fully submerged? It means actually just getting fully submerged. How much amount of weight you have to add on is what the question is asking. Okay, everyone. So what is happening here? You have a body in the liquid, which was earlier only partially submerged, something of this sort. Okay, it's a cubical body. If you take the same body but start putting some mass over it to reach here, okay, to reach here, how much amount of this mass m has to be added is what they're asking. So here what is happening? The buoyant force is different. Here the buoyant force is different. Here the total weight acting is capital mg, and here the weight which is acting is capital M plus small m into g. But here only 30% of the volume is inside. Here 100% of the volume is now inside. Fine. So let's see if we can think about it. Giving you guys complete 2 seconds for it. 2 minutes for it, and your time starts in 3, 2, and 1. Okay, 60 seconds remaining, 1 minute remaining, everyone. In both the cases, the body is floating, by the way. Okay, last 5 seconds now. And the time is up. Let's see. Wow, that is surprising. Really surprising that the people in the fastest finger list, almost everybody got this. Surprising, really surprised. So guys, in the first case, I will say that the buoyant force which is acting on the body is density of the liquid. Okay, that is given to us as 1000. Okay. Into volume of the body. And how do I write the volume of the body? It is 0.5 into 0.5 into 0.5. That means if I write it as 125 into 10 to the power minus 3. So it is 125 into 10 to the power minus 3, the entire volume. Out of that, only 30% is inside. So only this much volume is inside of the body into G value. Okay, so this is equal to mg. Right? But now if I speak about FP dash, it's the same density of the liquid, but now it is entirely the complete volume of the body which is inside. 100% into G, and this is M plus M into G. Is the logic clear to all of you so far? Earlier, the buoyant force was only because of 30% submersion of the body, and in the second case, it is 100% submerging of the body itself. Okay, so have a look, everyone. So I'm writing the same thing here. So from here, first part, if I cancel the G value, you can see that this will be 10 to the power minus 3. We can write it here also. 10 to the power minus 3, and the value of density, this is going to cancel this out. This is going to cancel this out. So 125 into 3 by 10, this G also got cancelled. So what do I have here is 125 into 3 by 10, and here it is only 125. That is what we get. The mass comes out to be 125 into 3 by 10. In the second case, when I cancel G value, when I cancel this 10 to the power, what do I get is m plus m, which is equal to 125. So if I put the value of m here, I get 125 into 3 by 10 plus small m, the mass that I'm interested in finding, is equal to 125. Taking this whole setup on the right hand side and simplifying it, what do I have is 125 minus 125 into 3 by 10. Taking 125 common, I have 1 minus 3 by 10, which is 7 by 10. When we do the maths, we get the answer as 87.5 kgs. Okay, so that's a JEE 2019 question that you just cracked. Congratulations to all of you. Okay, so next question, all of you guys. This one, I've given you almost every hint that I can. It says that a wooden block floating in a bucket of water has 4/5 of its volume submerged. So 4/5 of the volume of the body is submerged, and when a certain amount of oil is poured in the bucket, it is found that the block is just under the oil surface with half of its volume in the oil, half of its volume in the water. So the density of oil relative to the water, that means rho oil by rho water, which we also call as the specific gravity of oil, how much that value is going to be. So I'm giving you the hint that in first case, it is 4 by 5 times of its volume, which is inside water. So its weight is being balanced only by the buoyant force of the water. When you simplify this, it is rho Vg of the body, which is equal to rho W 4 by 5 V into G. In the second case, the entire body's weight is this time handled by two buoyant forces, with half of the volume in air oil and half of the volume in water. So you have these two equations to use and to find out the value of rho oil by rho water. I'm giving you guys once again 2 minutes, and the time starts in 3, 2, and 1. Come on, everyone. Don't try to rush. Try to be more thoughtful about the question. You all can do it. It's not very difficult. Okay? 20 seconds remaining, everyone. Okay, so let's see. Okay, that's nice. That's nice. Almost 50% people got this right. So guys, this is actually very simple, because from here I'm giving you a biggest hint that you can get the density of the body in terms of density of water. So from here, density of the body comes out to be 4 by 5 times the density of water, and that you can put over here. So you can see that G will get cancelled. The rho can be written as 4 by 5, and V is also getting cancelled by the way. Yes. So 4 by 5 into density of water is going to be density of oil. Just a second, guys. For some time, just my audio. So rho oil plus rho water divided by 2. Okay, everyone. So from here, you can easily find out the density of the oil. You can carry on from here itself. Okay, guys. Okay, so 4 by 5. If I take this 2 on the left hand side, I have 8 by 5 rho W equal to rho oil plus rho W. We are interested in rho W, right? Sorry, rho oil. So rho oil comes out to be 8 by 5 rho W minus rho W. That's basically 3 by 5 rho W. So rho oil by rho water is what we were interested in finding. Comes out to be 3 by 5, which is nothing but 0.6. That's basically the relative density or specific gravity of this oil with respect to water. We have found that. Okay, everyone. Cool. Guys, first of all, really sorry, आज सारी चीजें मेरे लिए बहुत नई है in terms of the setup, in terms of the place, in terms of the side light cutoff, and the background and everything. I hope that you guys are still able to. Okay, so there's a reason why I'm not able to go to the office today. I was taking my YouTube session from Harsh's class, and after that, it is heavily raining in Bangalore. Maybe those who are in Bangalore, they know this. So I could not travel to my office. It's a far away place from here, so that's why we had to like, do this makeshift. Okay, but I promise from next time onwards, we will definitely have our usual setup back. Okay, this is not my house here. Okay, I don't even know Kana. I was just looking at the screen. Okay, everyone, maybe some food delivery guy. Okay, chalo, everyone, a few more slides for us. Though the laptop battery is also like challenging me now. Anyway, wait, I'm not parting here. I was supposed to be gone. Okay. Yes. Okay, everyone. One more question for all of you guys to try. Have a look, everyone. So this question is similar to the question where we had a spring balance to which a body is connected and the actual weight of the body was taken. So similar thing is said that tank containing water of mass M, okay, is placed on a weighing machine. Okay, so basically we have a tank which has some mass M, which is placed on a weighing machine, and a stone of weight W is hung and lowered in water without touching the sides. So there is a stone which you are dipping inside, which is going to experience the buoyant force. Okay, so if the volume of the stone is V and the density of water is rho, what do you think will be the reading of the weighing machine? Will the reading of the weighing machine increase? Will it decrease? A little bit of laws of motion will be required here. Okay, so start thinking about it. I'm setting up the quiz over here for all of you. Is it zoomed? Okay, so everyone, I hope that now the slide is clearly visible to all of you guys. And setting up the quiz already, and we'll give you guys 90 seconds for this, and the time starts in 3, 2, and 1. Try to find out the reading of the weighing machine. Will it be mg equal to the weight of the container, which was earlier there, or if you are putting a stone inside, will it affect, will it not affect? It is not even touching the walls of the container. So let's see how many of you still remember the laws of motion. Last 15 seconds approaching, everyone. Okay, and that's nice. Let's see how it was supposed to be done. So everyone, switching on the chart also. So will the stone experience a buy and force upward or not? First question. Will the stone experience the buy and force or not, irrespective whether the beaker is placed on a weighing machine or not? Forget about the weighing machine. Imagine there's no weighing machine. There's a container which has liquid. You're dipping something inside. Will it experience the weighing, the weighing, this thing, the buy and force or not? It will, right? But now, who's applying this buy and force on the stone? Who's applying this buy and force on the stone? Water. Does water have mass? Right. So if water is applying a force on the stone, should there be a force applied by the stone on the water also? Should there be a force applied by the stone on the water also or not? What do we call such two forces? Action, reaction, absolutely. So same magnitude force as that of buy and force will be applied on the liquid. Are you getting my point? And this buy and force is adding on to the mg of the liquid. Are you guys getting it or not? Are you guys getting it or not? Logically. Right? So what is the net downward force acting now? Now the net downward force acting is mg plus fb. So the reading of the weighing machine should increase. Okay? That is why the answer will come out to be mg plus rho vg. So this is basically mg plus rho into v into g. Okay? A weighing machine, is it taking the weight of the stone or of the liquid? Weighing machine is taking the reading of the weight of the liquid or the stone. Do you not remember the contact forces? Do you guys not remember the contact forces? So when there is no contact between the weighing machine and the stone, there is no direct force which is applied by the stone on the weighing machine. What is the body which is touching the weighing machine? It is container. It is container, and container is experiencing the weight of the liquid, and now the buy and force is also being applied, or the magnitude of the force is applied in the downward force along with the weight of the container liquid is the buy and force का magnitude. Okay, everyone? The tension of the spring, you guys are not understanding. This is basically the container. This is the free body diagram of the container. Container has nothing to do with the string. If I draw the free body diagram of the stone, then stone has its own weight acting downward. It has only weight acting downward, and it will have a tension force and a buy and force acting upward. So ये हो जाएगा the free body diagram of the stone. But we are not talking about stone here. Okay, is that clear? The container is not filled to the top, Mustafa. The container is not filled to the top. Okay, doubt clear for everyone? Okay, now I am in a dilemma right now. Should I show you guys the last question, which is the question of the day, or should I not? Because the laptop's battery is now at 10%. Not that I don't want to. It's only because of the possibility that during that question solving only the battery might just give up. Okay, so we'll do one thing. At least I'll show you the question. You guys will start solving. Hopefully the battery will support and we'll be able to complete the question. Okay, everyone is okay with it? We have an inverter at this place, but that is being used in that room where Harsha is taking a class right now. For those who have joined us like later on, and in Indian Standard Time, many people join the sessions and meetings in Indian Standard Time, which is like 45 minutes late. You know? So for those people, I can't keep on giving the explanation. You know? Chalo. Yes. Everybody. So the question of the day, and it's a really good question. It says that we have a cube of wood which is supporting 200 grams mass, and it is just floating in water, completely submerged. So look at the diagram also. There is a wooden piece, okay, and say its density is rho s, and it is cubical shape, so L cross L cross L, and it has a 2.2 kg mass or 200 grams mass which is being put over it. Okay, so that it's completely submerged. The stone is not submerged; only the wooden block is submerged. Remember that the stone and the wooden block is just at the just at the free surface. It is just submerged. That's what it means. Now, when this mass will be removed, so we know that the wooden block will rise up. We have done a previous question or a question where just suppose it was done. We wanted to find out how much mass should be placed so that the body just submerges. So when the mass is removed, the cubical block rises up by 2 centimeters. Okay? So this block is going to rise up by 2 centimeters above the water level. You have to find the size of the cube. That means you have to find out L cross L cross L, how much this is going to be. Okay, so I am going to set up the quiz, but I'm going to give you guys complete 4 minutes for this question. And that is why I was under dilemma whether should I give this question as quiz or not because of the battery of the laptop. But the point is now I'm going to give you guys 4 minutes, which are going to start in 3, 2, and 1. So 4 minutes have started, and you know the timer can only be of 2 minutes. So I'll set up the timer in the last 2 minutes here for all of you. Okay, everyone, start solving. This is the last question of the day also, fortunately. I did not know that today is going to be a situation like this. Okay, everyone. 30 seconds are gone. You still have 3.5 minutes left with you. Trying to save the battery as much as I can. Okay, everyone, and in 3, 2, and 1, we're going to start the quiz. Okay, already people have started responding. Sir, you can use your phone for class. As in, you want me to teach from my phone? And how do I connect this to my phone to teach you guys? Huh? And don't worry, I'm not cutting off on anything that was supposed to be taught today. Okay? It is more of the laptop's battery issue and overall power connections, because of which the trouble we are facing today. Okay? Okay, last 30 seconds, everyone. Last 10 seconds, guys. Okay, and time's up. Let's see. Wow, that's nice. At least the fastest fingerless people are solving the questions religiously. So, guys, the thing is very simple. In the first case, it's the weight of the block and the weight of the cube, which will be balanced by the buoyant force. And in the second one, it is only the weight of the wooden block, which will be balanced by the buoyant force. But in the first case, here, the volume submerged. Okay. In this case, the volume submerged, let's call it V dash, it's going to be L cube, complete volume inside. But here, the V dash value is going to be L square into L minus H. The base area is completely inside, but the height which is inside is only L minus H. That's basically the catch. Okay. So this is what is going to happen here. In the first case, it is M plus M into G, the entire weight of block plus wooden block plus this block. Okay, the box plus wooden block is equal to the L cube into rho into G, means V dash rho G. In the second case, it is only Mg, the weight of the wooden block, which is being balanced by L square, L plus H into rho into G. Do you guys understand the logic here? Quickly in the chat box. Everyone understand the logic? We want to find out the value of L. Okay, cool. So chalo, jaldi jaldi soch samajh lete hain. So if we write the capital M plus small m, capital M is going to be the volume of the cubical body of the wall. Okay, the cubical body, my cursor has already started shaking because of the low battery. So L cube is the volume of the wooden block into density of the solid body of the wood plus directly the mass of the block above it is placed into G. This is equal to the buoyant force. L cube into rho into G. G gets cancelled. So what do I get from here? Then I can say that L cube into rho S. I take this 0.2 on the right hand side. I have L cube into rho minus 0.2. So this is my equation number 1. On the other side, L cube into density. Now that only the mass of the wooden block is being balanced. This is equal to the volume submerged. L square into L minus H into rho into G. G again got cancelled. So from here, L cube into rho S comes out to be L square into L minus H into simple rho. So I can see that I can equate these two equations very easily. Right, everyone? So when I equate that, multiply this L cube inside, I will have L square into L becoming L cube. L square into H is L square H into rho. L cube rho and L cube rho gets cancelled. I have minus and minus also cancelling. So from here, L square can be written as 0.2 by rho into H. This rho is the density of the liquid. That means water. Okay. So that is why 0.2 divided by density of water into the height of the liquid of the wooden block coming up. That was 2 centimeters. So 2 into 10 to the power minus 2. So when we simplify this, it comes out to be simply 2 into 10 to the power minus 1, this thing, and this is 2 into 10 to the power 1. So this also goes up, becomes 10 to the power minus 2. 2 and 2 got cancelled. So we have 10 to the power minus 2 as L square. L comes out to be 10 to the power minus 1 meters, which is nothing but 100 by 10 centimeters, or simply 10 centimeters is what we get. Okay, everyone? So that is why the block is of the size 10 into 10 into 10 centimeter cube. Okay, everyone? So the answer comes out to be option D. Okay, cool. So before the battery failed us, we have completed the session also. Let me quickly show you the leaderboard, everyone. So congratulations to Adish, Kalai, and Emily, the top 3. Then we have Harsh, Nihal, Ansh, Krish, Anushka, Shivank, Nikhil, Sanidhya, Aditya, Adi, Saeed, and Rani on the leaderboard. Congratulations, all of you. Well done. Let me quickly give you this. Okay, maybe by this time the battery might just collapse anytime. Okay, all of you. Great job. Well done. Good. Successfully completed. And once again, really sorry guys that we could not, have the session in the usual light settings and background settings because of so many reasons. Okay. Harsh sir का session चल रहा है. That's why. Harsh sir is taking his own class. Okay. तो हर्ष सर से तुम लोग definitely YouTube पे मिल सकते हो. आज हम लोग सब साथ में थे ही वैसे भी. ठीक है, everyone. So from next week onwards, we'll have our usual session and our usual settings. I can't give you the room tour. It is not my house. That's not my liberty. So that is why you'll have to pardon me. You can ask Harsh sir to give the tour of his own house. Okay. Thank you, everyone. I hope that you guys understand that today's was an special circumstances because of which I had to take a session from Harsh sir's place. Okay. Cool. Chalo, everyone, before the battery dies out, let's sign off. Next time जब मिलेंगे तो पूरी कमी पूरी कर लेंगे. We will speak after the class for longer duration. ठीक है? No, I don't like to take sessions like this where I'm not able to be visible and not in the zone where I usually like to be. But that's how it is. No, I'm not saying we were taking a YouTube session together. That's why. Okay? Yes. Chalo, everyone. I'll have to sign off. Okay? And the others can explain, the others who are asking that why session is getting ended today early. Okay, everyone, this is one of a kind time when this happens. Otherwise, you know that somebody would boycott. Okay, that's okay. ठीक, chalo, everyone. Signing off. Thank you, Mrityunjay sir. Thank you, everybody, for bearing with me today. I'll see you guys next week. We'll be back with a bang. And till then, take care. Bye-bye. Hasta la vista. Sayonara. Bye-bye, guys. Signing off.